is you're actually supposed to write down. So everything I'm about to do, I would recommend you don't write it down. This isn't like something that's on the test or anything like that. I'm just trying to give you some motivation as to where that formula comes from that you're going to get to use. The formula will be given to you. You don't have to memorize it or anything. So you just have to choose among your tables which one applies where. Okay, so here's the idea that we have. We have two populations. Oh, we're doing proportions. Two population proportions. Population proportion here. And then we have another population. And then we have another population proportion. And these are independent populations. Independent of each other. All right, well, some notation. One of the hardest things about this chapter is so many little variables running around and so much notation happening. So we're going to call this population 1. So I'm going to put a little subscript there to mean 1. And so this one would be population number 2. And so I'll put a little subscript in there. Okay, so this is the population. Like this could be of all Californians, what proportion are planning on voting for anybody, just participating in this election process in November? What proportion are actually going to vote for somebody this November in California? What about a different population? This could be population of Texas. What proportion of their citizens are going to participate in the election process? So two different populations that are independent of each other. If I randomly pick one Californian and figure out whether that Californian is going to participate in the election process in November, that's completely independent as to whether I pick one Texan randomly and say, are you going to vote for somebody, anybody this November? Yes? Okay, so we got two populations. So what we're going to do is we're going to take samples of a certain size. So let's say I take samples of a certain size here. And just for the purposes of giving you the idea, I'm just going to make up some random numbers here. So let's say, what do you think it is? What proportion of Californians do you think are going to participate in the election process in November? Just make some up. 60%, all right. 60% of Californians are going to participate, vote for somebody, show up to the polls. What about Texas?
80.
Okay, all right, so they're more active over there. All right, so maybe that's 80% over there. We're going to take a sample. Now this sample, we're going to call it n sub 1 to indicate that it's the sample size of samples that are coming from this population. Let's say that that sample size is 25. Just picking a number. All right, now let's say we take a sample from over here. They don't necessarily have to be the same sample size. Let's make it 34. So every time I pick a group, it'll be a group of size 25. And so that group is going to have a sample proportion that's going to be equal to x sub 1 over n sub 1. Where x sub 1 is how many people in my particular sample out of the 25 are going to participate in the election process. Okay? So every time I take a sample, I'll get an answer from here. Like let's say, for example, that in this first one I get 4 out of 25. Ooh, okay, so that'll be equal to 16%. Right? And then over here, in this particular sample, let's say I get some sample that's p hat equals to 20%.
Would it be p hat sub 2?
Ah, good. That's what I was going to point at. We got to be careful with the notation because now it can get confusing. So we have to be consistent that here we're going to call that p sub 1, p hat sub 1, p hat sub 2. Good. All right. Every single time we take samples, we'll get different p-values. So p hat 1 over here, it might be, well, these were way low, weren't they? How about one time we get 50% there, and another time over here, oops, why did I put a 2 there? 1, 2. The second sample we get from there, maybe this one's 90% in my sample, and so on and so forth, and so on and so forth. We're good so far? Okay, we got two different populations. This is what we're going to do. We're going to subtract them. We're going to consider this. Let's think about P1 minus P2 hat. So for every one of these values, we're going to take these results here, so it'll be 0.16 minus 0.20, which gives me negative 0.04. Now remember, a proportion can never be negative, but this is not a proportion, this is a difference of proportions, so I'm allowed to have a negative value. A negative value just means that this one was bigger than that one, and that's why it ended up being negative. Got it? Okay, so we do that for each one of these. So this one is going to be equal to 0.50 minus 0.90, giving me negative 0.40, and so on and so forth, right? And we do that over and over and over again. And we end up with all these numbers here, sometimes positive, sometimes negative, depending on which one was bigger, which one was smaller. And when we graph all of these, what do you suspect that's going to give us?
A line.
A nice normal distribution, right? Normal distributions appear in a lot of things in our universe, right? We didn't invent them. We just noticed that this happens, right? Nobody sat down and decided that this is the way it works. We discovered that this is the way it works. This is what happens when you do this. If I was going to really do this and put a giant population that has 80% of something, another giant population that has 60% of something, I randomly took samples of this size, randomly took samples of that size, subtracted their proportions, graphed those values, right? This would be some number on here. Negative 0.04, and over here I'd have negative 0.40, and so on and so forth, and some of them would be positive. So this would be a nice normal distribution, where each one of these values in here would represent a p hat 1 minus a p hat 2, right? Kind of in parentheses. Each one of these dots represents the difference between two proportions. Is everyone with me so far?
Does it matter, you
Yes.
have to do always one first, or does it matter like which?
It doesn't matter which one you do, but you just have to be consistent about it and keep track of it. So normally we just do p hats of 1 minus p hats of 2. Though it doesn't really matter if you do it the other way around, you just got to keep track of where it is. And ultimately when you translate your information, if you get a number that's positive, well, you got to go back and decide which one was the bigger one based on how you subtracted them. Okay, so now where's the center of this thing? All right, so we have to have a mu sub p hat 1 minus p hat 2. Right, it kind of sticks to our tradition of putting the little subscript there to mean 1. We had like x bar or p hat. Now we have a p hat sub 1 minus a p hat sub 2, which is very ugly. But this is equal to what? It's going to be equal to p1 minus p2, right? These proportions. So in this particular example, it would be equal to negative 0.2, the way I wrote it, right? But in general, it's equal to p1 minus p2. And what's the standard deviation of this thing? Well, that's ugly. P hat 1 minus p hat 2. This is equal to p1 q1 over n1 plus p2 q2 over n2, square root of that whole thing. Okay? Remember, this was sort of the equation for the standard deviation when we had one population. So this summation of the two and the square root of the whole thing is the standard deviation of the distribution when we have two populations. It looks sort of familiar, right? Kind of, sort of familiar. All right, so now note there's no hats on here. These are the actual population values, these guys. P1, P2, right? That's what these are. There's no hats on them. That's not about the sample. So in the examples that we're going to do, though, we are not going to know what this is, right? We're not going to know what they are. So it's going to be unknown. But we're going to make, the hypothesis statement that we're going to be working with just in this class is going to be always that the two population proportions are equal to each other. We don't know what they are, but we're going to assume that they equal to each other. And so if we don't know what they are, but they equal each other, what's going to happen when I subtract them?
They're going to be 0.
It's going to be 0. So for us, because we assume, so I'm going to put it here, H naught for us is going to be that P1 equals to P2. That's always our H naught for us in here, right? Anything different than that is more complicated and is something that you'd have to study in a different math class. Okay, so always equal, which means that when I subtract them, it equals to 0. P1 minus P2 equals to 0. All right. So that takes care of that, because for me it's always going to be 0. But what about that?
0 over...
Well, if you don't know what they are, but I mean you're just assuming that they're equal to each other, but you don't know what they are, so the best thing for us to do is to use our sample data. Got it? So there'll be some sample value given, right? So we'll have some given value here, given some x sub 1 equals to 8 and some n value, so we can find p hat 1 over here, 8 over 25, for example. And then there'll be some other value for this distribution. X sub 2 will be equal to, I don't know, 9. And so we can find some p hats of 2 like this, 9 over 34, right? So this will be given. And so this really represents one value here. When I find this proportion minus this proportion, it'll be some value in this distribution, the difference of the two proportions, okay? And now we're going to use those numbers to approximate this. And this is how we're going to do it. We're going to use this formula. P hat with no little number. P sub 1 is this one. P sub 2 is that one. Now P hat with no little number is sort of a pooled proportion. We're going to take all of it together and say that this is equal to x sub 1 plus x sub 2 all over n sub 1 plus n sub 2. And that will be the value that we're going to replace here. So this is going to be approximately equal to p hat 1 minus p hat, right, which is the q. So we're using it to replace p there. That's this number there. And then all over n1 plus, in fact, let me write it this way. Let's go to black. And then I'll put p in blue. So this is approximately equal to p hat 1 minus p hat p hat all over n sub 1 plus, and then p hat, and then 1 minus p hat all over n sub 2, and square root of that whole thing. So for each of these p's, I replaced it with this p hat right here, this pooled proportion. And then the q's are, of course, the complement, so 1 minus p hat. So really this and this are the same. So the formula that you run into just kind of pulls it off to the side and writes it as a separate value. So this is equal to p hat 1 minus p hat inside a root. In fact, I better write it over here. I think I'm running out of space here. It's equal to p hat 1 minus p hat times 1 over n sub 1 plus 1 over n sub 2. And that's inside a root, and that's inside a root. So that's the way the formula is given in the book. It's this. P hat 1 minus p hat times 1 over n plus 1 over n 2, where p hats are really these things. Good? Questions, comments, issues? Questions, comments, issues? Maybe. Alright, so back to this thing. This is equal to 40%, 0.40. And then over here, I don't know, what is 9 divided by? Well, that's actually really low compared to the 80, isn't it? Or whatever. 9 divided by 34 is equal to like 26%. 26%. Okay, so then I subtract them in this order. I end up with negative 14%. So I end up with 0.40 minus 0.26, which equals to negative 0.14. So negative 14% is going to be a value on here somewhere, maybe there, at negative 0.14. And so the area I'm looking for is going to be that. Okay, so the center will always be 0 for us, because our null hypothesis is that they equal each other, so that'll be 0. However, this is not the standard normal distribution, because this is not going to be 1, not necessarily. Right? It's going to be some random number that's not necessarily 1. So therefore, to find it, we can standardize it. To standardize it, we find the z value. The z value is going to be equal to this distance divided by its standard deviation, right? And that's the formula that you're going to get. Z sub naught is equal to, now this distance is going to be this number, which we found by subtracting the p hats. So it's equal to p sub 1 hat minus p sub 2 hat. That's the difference in our sample proportions. That's these numbers right here. Right, this is p1 hat, p hat 2. And then minus the mean, which is this, p1 minus p2 without the hats. These are the proportions from our population. Well, for us, it's always going to be 0, but that's the general formula for it. Divided by this thing, which is going to be equal to p hat 1 minus p hat 1 over n sub 1 plus 1 over n sub 2, square to that whole thing, square to that whole thing. Okay? So this is the formula that's given to you. You don't have to memorize this, but when it comes time to do the actual problem, boom, you go right to this guy. And this is easy. This is just going to be a 0. Easy. This is our proportion from the first sample, our proportion from the second population. And then this is the pooled proportion, which is given by that formula right there. And so this equation will automatically give you the z-value in a standard normal distribution, so you can find the area proportionally equivalent to the area that you actually want that gives you the probability of getting such a result. Okay? And so from there you can just use normal CDF with mu of 0 and a standard deviation of 1. Okay, so that's it for the concept idea. Any questions about the concept before we do an example? And I'll show you what you actually write down when you want to solve one of these. We're good? Kind of? Maybe? Sort of?